Hey there, Mr. Weaver here, and this is Module 9, Lesson 2, Transformations of Exponential Functions. After this lesson, you need to be able to apply translations, dilations, and reflections to exponential functions, and you need to be able to use transformations to identify exponential functions from their graphs and to write equations of exponential functions. Let's learn translations of exponential functions. Our key concepts here are the vertical translations of exponential functions and horizontal translations. As we saw in previous modules, a translation just moves the function up and down or left and right. When we did it with linear functions, sometimes moving it up and down or left and right looked the same. With exponential functions, you're definitely going to be able to tell if the function was shifted up and down or if it was shifted left and right. So for vertical translations, just like with linear, you are going to have a value of k that is added on to the end. If k is greater than 0, meaning it's positive, then it's going to be shifted up. If k is less than 0, where you would see it as minus a number, then that function is going to be shifted down. For the horizontal translations, this is going to show in the exponent, and it's going to be the opposite of what you see. So if it is greater than 0, and you see minus h, then you're actually going to move it to the right. Whereas if h is less than 0, and you would actually see like x plus h in the exponent, so b times x plus h, then it's going to shift to the left. So backwards of what you see. Example 1, vertical translations of exponential functions. Describe the translation in g of x equals 2 to the x plus 3 as it relates to the graph of the parent function f of x equals 2 to the x. So first, if you remember, parent function just means it's the most basic form of that function. So here we can see that the only difference between f of x, which is our original, and g of x is this plus 3 that is tacked on to the end. So that is the k value. If it's at the end, that is going to affect your output, meaning it's going to move it up or down because output is your y values. Since that value is greater than 0, then this is going to be translated 3 units up. And we can see right there, plus 3, moving it 3 units up. If we look at the graph, we can tell here's our original y-intercept, here's our new y-intercept. How many units was that? 3. 3 units up. And if we check other points as well, they are all translated 3 units up. Example 2, horizontal translations of exponential functions. Describe the translation in g of x equals 3 to the x plus 1 power as it relates to the graph of the parent function f of x equals 3 to the x. Our only difference there is that plus 1 in the exponent. That's telling us that it is going to be moving to the left or right, horizontal. Again, it's going to be the opposite of what we see. So here, for that, we are really saying that h is subtracted from x before. So if you see it in the exponent, that actually affects the input values, which is why it moves it left or right. Then we see that the value of h is less than 1. Remember, opposite of what you see. So this would shift it 1 unit to the left. We see plus 1, so we're going to go left 1. Essentially, minus 1. If we look at the graph, here, we can look and we can see that everything was shifted 1 space earlier than where it was originally. Example 3, multiple translations of exponential functions. Describe the translation in g of x equals 1/2 to the x minus 2 minus 4 as it relates to the graph of the parent function f of x equals 1/2 to the x power. So here we have 2 things happening. We can see in the exponent there's a minus 2, and at the end we have a minus 4. So that minus 2, we would do that before, and since it's the opposite, minus 2 is actually greater than 0, which means it's going to be translated 2 units to the right. As for the k value, that minus 4 at the end, it's going to happen after we plug in our x value and calculate that part out. So this time, the k value is the same. It is less than 0. So this is going to be translated 4 units down. So as you're going through, you're going to see many instances of multiple translations. Remember, you're doing the opposite of your x value, but the same as your k value. If we look at our graph, we can see both things are happening. So originally in f of x, let's say that point right there, compared to that point right there in g of x. It was shifted to the right 2 and 4 units down. Check your understanding. Look at the translation given and describe how it relates to its parent function. Pause the video now and complete the check. Check your answer. You should have said that it went 1 unit to the left and 8 units down. We can see right here, plus 1, we're really thinking it's going to go to the right, but it's the opposite to the left, and the same as k, so it is going down. Let's learn dilations of exponential functions. The first part of our key concept here is going to be vertical dilations. So when we have a dilation, we are stretching the function either vertically, as we have here, or horizontally. For our dilations, we are either stretching or compressing, and it's going to be by this a value. So the starting value is actually stretching it or compressing the function, since the general parent function is usually 1 times 2 to the x. So if we have this as a 1, it's not being stretched or compressed at all. But if it's anything else, it's either going to start with a higher y-intercept or it's going to be compressed to a lower y-intercept. So if a is greater than 0, or the absolute value, then it's going to be stretched, meaning it's starting farther away from the x-axis. If it's between 0 and 1, so a decimal or a fraction, then it's going to be compressed, and it will end up starting, the y-intercept will be closer to the x-axis. For horizontal dilations, it's either being stretched or compressed toward or away from the y-axis. And for horizontal dilations, it's going to be up here in the exponent. If the a value here is greater than 0, so meaning like this said would be 2, then it's going to be being compressed horizontally towards the y-axis, which actually means it's going to go up or down faster. If our value is a fraction, kind of like we saw in the last lesson with our half-life, where it took 5 hours for the caffeine to disappear, it will get stretched away from the axis, meaning it's going to take longer for the values to change. Example 6, vertical dilations of exponential functions. Describe the dilation in g of x equals 1/4 times 3 to the x as it relates to the parent function of f of x equals 3 to the x. So our parent function here was 3 to the x. The only difference is this 1/4 out front. That is your a value. So instead of it starting at 1 with our y-intercept, our a value is going to make the y-intercept start at 1/4. Figuring out if this is stretching it vertically or horizontally, we're going to look at where that 1/4 is positioned. So since it's out front, it's going to be multiplied after we evaluate. And since 1/4 is between 0 and 1, then this is going to be a compression vertically by a factor of 1/4. So it actually shrunk down towards the x-axis and is now 1/4 of the way as compared to where it started. If this had been 4, then we would have started up our y-intercept up here at 4, and it would have looked the same, but we are farther away from the x-axis, so that would be a vertical stretch. And more likely than not, you are going to see vertical compressions and stretches compared to horizontal, so that is the only example we're going to do here. Let's learn reflections of exponential functions. Our key concept then are our reflections across the x-axis or our reflections across the y-axis. In exponential functions, reflections are very common to see. For a reflection, all you are doing is really multiplying by a negative somewhere to make it the opposite. So in a reflection across the x-axis, so it's reflecting down over the x-axis, then you're going to see a negative out front of the function. What this means is every coordinate of f of x will now be the opposite y coordinate. So it will reflect it down. Our other type of reflection can be across the y-axis, where you are going to be reflecting it sideways. When this happens, the negative is affecting the x value before you multiply it. So usually it's going to be up here in the exponent like negative x. And what that means is every x coordinate is going to change to the opposite, while the y coordinates will stay the same. Example 10, vertical reflections of exponential functions. Describe how the graph of g of x equals -3 times 2 to the x is related to the parent function f of x equals 2 to the x. So first, we can see there's a negative out front telling us that it's been reflected, and actually this was also dilated by a factor of 3. So first it was multiplied by -1, and since it's outside of the x value, that means it's being done after, and thinking about the a value is 3, so it's greater than 1, which means that this function was stretched vertically and reflected across the x-axis. So if we think about g of x, if this was positive, it would be like up here somewhere, it got stretched away, and then it got flipped over. So two things actually happened to this. Got stretched up and then flipped over. Example 11, horizontal reflections of exponential functions. Describe how the graph of g of x equals 3 to the -2x is related to the parent function 3 to the x. So again, this one, we can see two things were happening in that exponent. There's the negative and the 2. Since those happen in the exponent, we need to do that before we multiply anything out. And since a is greater than 1, that would mean that it's compressed horizontally. And because it's in the exponent, it is going to be reflected across the y-axis. So if we look here at what happened, before we flipped it, it actually got in a little bit tighter towards that y-axis, and then we flipped it over. Every x value was doubled first, so it's really changing twice as fast, and then the negative part means we're flipping it, so all the x values are the opposite of what they were. Check your understanding. Match each function with its graph. Pause the video now and complete the check. Check your answer. So first of all, graph 1 matches with D, 2 with C, 3 with A, and 4 with B. Realistically, you could just type all of these into Desmos and see what graph matches what, but let's look at how we can figure this out without that. So first of all, in the first one, we just see a negative out front, which is telling us that it's going to be flipped downward. So 3 to the x usually looks like that. So if it's flipped downward, now it must be flipped like that. So D would be the one that matches. For number 2, we have a factor of 1/3, which tells us that it's decaying in the first place. And there's a negative out front of x, so it should be reflecting sideways. So it would be going the opposite of what we see, which is letter C. We have that pattern going right here. For number 3, the 1/3 again is going to look like that originally as it's a decay function, but the negative out front is going to reflect it downward. So it would just be reflecting the opposite, and that shape is A. Finally, 3 to the positive x looks like this normally. If it's being reflected with a negative in front of the x, it's going sideways, so it would look like that, which is B. Let's learn transformations of exponential functions. The general form of an exponential function is f of x equals a times b to the x minus h plus k, where a, h, and k are called parameters that dilate, reflect, or translate a parent function with base b. The value of a is going to stretch or compress the parent graph. When a is negative, it's going to reflect across the x-axis, and usually that's downward. The value of h shifts or translates it left or right. Remember, that's the opposite of what you see. And then the value of k shifts it up or down, and that's going to be the same as whatever sign you see there. Positive is up, negative is down. Example 12, multiple transformations of exponential functions. Describe how the graph of g of x is related to the graph of f of x. So here we have a bunch of things happening. We have a negative, we have a dilation, we have a translation, and another translation. So first, we can see that it's reflected across the x-axis because there's a negative out front, and it's going to be compressed vertically based on this 1/2 here. Since it's out front, it's a vertical dilation, and because it's between 0 and 1, it's going to be compressed, and that's by 1/2. Then if we look at our h value, which is 2, and it's the opposite of what we think, so if we see -2, we have to go 2 units to the right. And then finally, that -1 means we're going to go 1 unit down. So this whole entire function was compressed vertically, reflected across the x-axis, and translated 2 units to the right and 1 unit down. Check your understanding. First, describe how the function of g of x relates to the function of f of x. Then, in part B, sketch the graph of the transformation. Pause the video now and complete the check. Let's check our answers for part A. So first, we can see that it was reflected across the x-axis by that negative out front. The 4 tells us it was stretched vertically. We have +5, which means it's going to go to the left 5, and -2, so it's going to go down 2. For the graph here, first of all, because it started as a half, it's going to be a decay function that looks like that. The reflection is going to flip it over, so now it was going to appear like that. It would shift to the left 5 units and down 2, also being stretched 4 units away from the x-axis. That's very complicated, so for this one, let's actually head over to Desmos and help us to figure out what it looks like. In Desmos, let's see what each of these transformations is going to do. So right now I have our original parent function graphed, which is just f of x equals 1/2 to the x power, where nothing is done to it. So as we go through, let's add things that happen to it. If we were to dilate it by a factor of 4, it's going to move it up 4. It's going to stretch it vertically. That negative out front is going to reflect it over the x-axis. We have a +5 in our exponent, and to do the +5 in the exponent, you're going to actually need to put it in parentheses. And we can see that now it is shifted 5 units to the left. And then we can do our -2 at the end, which is going to shift it down 2 units. And that -2 at the end also shifts the asymptote from 0 down to -2. So if you're asking about key features, with a function that has a lot of transformations, the asymptote is one that particularly changes along with the range, since that depended on the asymptote.